Hello guys, welcome back to my channel Gamma Di Gamma. In this video I have for you a very nice integral that I actually encountered, not in some Olympiad problem sets or in any other Instagram posts or any other YouTube channels. I actually encountered this when I was scouring the internet for more math content. It was in a preprint that was on the ResearchGate. So I will credit the author if someone asks me, and I certainly haven't discovered this nice integral. But regardless, it's pretty nice. So let's get on with it. First of all, let me define the integral. It's I, it's an n-dimensional integral, so it has n nested integrals in it. And the region we are integrating over is actually the n-dimensional equivalent of a square, a unit square, because all the lengths are 0 to 1, basically 1. So we have actually the fractional part. In the numerator, we have a product from x1 to xn minus 1 divided by xn, where all these 1 to n are basically the different coordinates of the space we're working with. You can think of them as n different variables of the space. So first of all, you might say, well, we don't really like the denominator. Can we get rid of it? And in fact, we can. So we can get rid of it by doing a substitution that sets 1 over x to the 1 over xn to xn. When I do that, and it's quite an elementary substitution, we have done it probably hundreds of times on this channel, we get xn squared in the denominator as the integration factor, as the factor from the differential element. And we have the fractional part of x1, x2 multiplied until xn. Notice the order of integration. We're emphasizing the integration on xn first, and you'll see why. So first of all, since we are on this xn integral, notice the bounds are from 1 to infinity. What we can do is we can sort of treat the x1, x2 until xn minus 1 as constants with respect to xn. In fact, they are. So what we can do is we can do a change of variables. So let's say xn goes to xn divided by x1 times x2 times until xn minus 1, where I'm going to denote the denominator as pn minus 1. So we end up with xn over pn minus 1, where pn minus 1 is actually just the product from 1 to n minus 1 of the xi. This is just convenient notation. There's nothing special about this product. So we can write our entire setup as n integrals, where the nth integral is actually going from pn minus 1 to infinity. The rest of them are going from 0 to 1. And then dxn to dx1. And we have pn minus 1, which came as the factor, the extra factor from the differential. Fractional part of xn divided by xn squared from before. Fair enough. Now we're going to do a very clever thing. We're going to split pn minus 1 to infinity, the interval of pn minus 1 to infinity, into pn minus 1 to 1 and 1 to infinity. You will see why this helps us in a moment. First of all, let's look at the first piece, the pn minus 1 to 1 integral in the dxn. Everything else is the same, so I'm not going to even bother repeating that for each of the integrals. Notice for the first integral, we have x1, x2 till xn minus 1 are bounded from 0 to 1 because the bounds of integration are from 0 to 1. That's the the obvious thing. Notice that the product of all these guys, so pn minus 1, which is the product of all these guys, x1, x2, xn minus 1, as we defined above, is going to be less than 1. right? Because all of these guys are less than or equal to 1. So even the product will be less than or equal to 1. This is just multiplying small things gives us even more small things, because you can treat these of the order 1 over n, where n is some arbitrary integer, and then you can see that you end up with 1 over, a product of arbitrary integers is also an arbitrary integers, but since that n in the denominator was large for all of these guys, you're gonna have 1 over some large number which is very small, less than or equal to 1. Okay, this was, how does this help us? Well, let's see. We have in the first integral, xn is actually bounded between Pn minus 1 and 1, which is because the bounds of the integration are that way. Fair enough. And then we know that Pn minus 1 is greater than or equal to 0. Just from this, because if all of these guys, if any one of these guys is 0, then we know Pn minus 1 will be 0. Fair enough. So if we take the fractional part of xn like we need in this integral, in this part, we get xn minus the floor function of xn. Now xn is just xn, so xn is as it is. The floor function of xn is actually going to be the integer, the nearest integer that's less than xn. So the nearest integer that's less than xn, according to this inequality, is 0. The only integers in that interval are 0 and 1. But we need, for the floor function, an integer that's smaller than xn. So that's 0. So we get 0 for the floor function, and we get the fractional part of xn is just xn. That helps us because there's no more complications resulting from the fractional part function. So we just get xn instead of the fractional part. So we can just remove the curly brackets. Now that's just the first integral. The second integral, however, we can split the interval from 1 to infinity as k to k plus 1, and then we sum from k equals 1 to m minus 1, and then take the limit as m goes to infinity. I'm going to repeat that. I'm going to sort of unpack all of that for you because that's a lot going on. So interval was from 1 to infinity. We can break 1 to infinity in terms of these integers, k to k plus 1. And where will we start from? Well, we'll start from 1, right? Because that's the lower bound in the original integral. So k equals 1. And then we end up at infinity. So infinity in this case, I'm going to call m. Because if you plug in m minus 1, which is the last, the bound of sum, we get m as the final integral upper bound. And we're taking m to infinity. So it's actually, if you combine all these integrals in the sum by linearity, you end up with 1 to m, where m goes to infinity, which is actually 1 to infinity. So I've broken the interval, summed over from 1 to m minus 1, where m goes to infinity. That's all I've done. I've just broken 1 to infinity in terms of adjacent integers. And you'll see why that's helpful, because now we know for each of these integrals for a fixed k is less than or equal to xn is less than or equal to k plus 1 from the bounds of the integration. And then the fractional part will just be xn minus floor of xn. Now the floor of xn in this interval will be k. So it's going to be xn minus k. That's nice. We can completely remove the curly brackets and replace them by xn minus k. So the first integral as it is, we can, I've just cancelled one factor of xn here. So xn cancels with the xn squared to give me xn. That's kind of obvious. Now we can take the limit and the sum outside. We have integral 0 to 1, 0 to 1, and then the xnth integral is k to k plus 1. And then we have this difference because of the xn minus k term. So where we have the xn, that will cancel one of the factors in the denominator. So we get Pn minus 1 over xn minus k times Pn minus 1 divided by xn squared. That's one term. That's why I've sort of square bracketed that. Moving on. What we can do is we can break down what Pn minus 1 is. Pn minus 1 is just the product of x1, x2 until xn minus 1. So what I'm going to do is I'm going to write each of those variables beside its corresponding integral. So what I mean by that is, if I have x1, right, in Pn minus 1, the first term in the product is x1, I'm going to write x1 under the x1 integral. So the x1 integral is on the outside, it's the very leftmost integral. So I'm going to write x1 like that. And now the next term in the Pn minus 1 was x2, so I'm going to write that under the x2 integral. And then the last term was the n minus 1, xn minus 1, which I'm going to write under the xn minus 1 integral like that. And then finally we just have, the usual nth integral. But now the Pn got distributed among its individual integrals. So we just have the dxn, the differential divided by xn, which was the only variable remaining. I'm also going to do this similar distribution and reorganization in those other two integrals that we have generated by the second term in purple. So it's going to be, take the limit and sum outside. 0 to 1 x1, 0 to 1 x2, ... till 0 to 1 xn minus 1. That's the first n minus 1 integrals. And then the last integral, the nth integral, is dxn over xn from k to k plus 1, minus, because now we have to deal with the k term, limit, wait, it seems I have forgotten a factor of k somewhere. Maybe I should correct that before I move on. Apologize for that. Okay, so we have limit, the sum, and then we have the k term that was there. We have x1, x2 under their integrals respectively till x minus xn minus 1, and then the last xnth integral, which is dxn over xn squared from k to k plus 1. Okay, now moving on, the first integral we can just integrate with respect to the xn. We get a natural log from 1 to Pn minus 1. So natural log of xn evaluated 1 minus evaluated at Pn minus 1. So that's just going to be minus natural log of Pn minus 1, because ln1 is 0. So we just have the ln Pn minus 1, and then the rest of them is the rest of it is just the same. Now the second integral we can evaluate is again going to be an ln of xn this time, evaluated kn, k plus 1 and k. And then the third integral is sum k equals 1 to m minus 1 of k. And then we have for the last integral we have minus 1 over xn evaluated k and k plus 1. Why am I getting a factor of 1/2 in the rest of them? Because I've integrated all of these other guys. So because there was no other dependence in both these last integrals, there was no dependence on the xn minus 1 until x1. I can just integrate them out eventually. So if I integrate xn first, I get x1 squared over 2 from 0 to 1, which is 1/2. Same thing here, 1/2 and 1/2. So I'm going to get n minus 1 1/2s. And similarly here as well, n minus 1 1/2s along with the last integral, which is ln xn here and minus 1 over xn here. I can't integrate each of these guys in the first integral. It's because ln of Pn minus 1 is a product of x1 to xn minus 1. So we can't really separate this out like we separated this out. There's still functional dependence on x1 to xn minus 1 inside this natural log, that term that got generated. So what I'm going to do is I'm going to realize that ln of Pn minus 1 is just ln of the product from I equals 1 to n minus 1 of xi, which because of the properties of the natural log, I can split up over a sum. So the sum is going from 1 to n minus 1. And then I can just write that out as ln x1 plus ln x2 plus dot 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 ln xn minus 1. Right, so this means that just from this first integral in pink here, we're getting n minus 1 more integrals. So I'm going to write each of those guys out. So for the first one, we have ln x1. I'm going to write that under the dx1 integral. So x1 times ln x1. The x1's from the original setup here, from the original distribution. And then x2 with nothing else on it, so dx2, and then so on, xn minus 1. So you kind of see a pattern, because now for the ln x2, x1 doesn't have anything, and so do the others, except for the x2 integral, which has x2 ln x2. And then so on for the last one, we have ln xn minus 1, xn minus 1 dxn minus 1, and then the rest of them are just integrals 0 to 1 x1, 0 to 1 x2, and so on. So what we're getting is, for each of those terms in this sum, we're getting one integral of a variable times natural log of that variable, and then we're getting n minus 2 integrals from 0 to 1 of a variable times evaluated d variable, basically. That's just the first term generated by the ln pn minus 1. What about the second and the third in the original setup? Well, we can just plug that in, so we get ln k plus 1 minus ln k, which I've written down here. And then similarly for the minus 1 over xn, we can plug those values in, the upper and lower bounds. I can factor the k that we had lingering to get 1 over k minus 1 over k plus 1 times k. Fair enough. Now, notice that this natural log sum from 1 to m minus 1 is actually telescoping, because if I write the terms out, so when k equals 1, we have an ln2 minus ln1, and then we have plus ln3 minus ln2, so on until ln m minus 1 minus ln m minus 2, and then ln m minus ln m minus 1. We see ln2 cancels with the right term of the next iteration, and then the pattern is that the right term cancels with the left term of the previous iteration. So ln m minus 1 cancels nicely with the term before it, but ln m and ln1 are the only tail terms, that the head and tail terms that remain uncancelled. ln1 is 0, so we can ignore that. We still have the ln m in the limit as m goes to infinity. As I said, the observation for the first integral was that we get one integral, which is over variable times natural log of variable from 0 to 1. And then we have n minus 2 integrals from 0 to 1 of a variable, which turns out to be 1/2, because xn minus 1 squared over 2 is from 0 to 1 is 1/2. So we get 1/2 to the n minus 2, because there were n minus 2 of those integrals. And then we have j equals 1 to n minus 1 of these integrals as well. We have n minus 1 of these x times ln x integrals as well. So the term that remains, as I said, is just ln m in the second term here. So ln m remains, and I can simplify this right here nicely, because if I take a common denominator here, I'm gonna get k plus 1 minus k over k times k plus 1, and the k's cancel out. So eventually I end up with 1 over k plus 1, k equals 1 to m minus 1. That's nice. We've compactified the form of the long integrals. Now let's just evaluate the first integral in white by integration by parts. So I'm integrating over the x variable and differentiating over the natural log. So xj squared over 2 ln xj 0 to 1 minus 1/2 0 to 1 xj dxj, all from j equals 1 to n minus 1, because there's n minus 1 of them, as we saw in this blue write-up. And in the other term, we can just reindex. So you see there's a k plus 1, we can reindex to get a k in the denominator, but that means we have to start the sum from 2 and end at m. Nothing else. And we have also pulled out a minus sign, which comes out like this, minus 1/2 to the n minus 1. Okay, now let's evaluate the first term here. So when we plug in 1, we get 0 because of the natural log, and at 0 we also get 0. I've done that L'Hopital's rule calculation down here. I'm gonna sort of skip over that because I'm assuming you know. So that means the first term completely vanishes. We just have this integral from 0 to 1 of xj, which we know by now, I'm sure you know, is 1/2, because xj squared over 2 from 0 to 1 is 1/2. So that 1/2 and this 1/2 will give us, but there's also another 1/2. So there's two 1/2s with a minus sign from the integration by parts, with this minus 1/2 to the n by 2. And then this is still being summed. Okay. So, and then in the rest of the terms, the second term is just as it is. All I've done here is just, you notice the sum starts from 2. I wanted it to start from 1. So what I've done is I've added and subtracted the first term. I've added and subtracted the k equals 1 term in this sum. So the k equals 1 term is 1. So subtracting 1 is, when I add 1, I can just include that in the sum. But then I'm subtracting 1 as well, right? I can pull the factors of 1/4, and then it becomes 1 over 2 to the n. Sum from j equals 1 to n minus 1 of 1, minus 1/2 to the n minus 1. Notice that this first term, k equals 1 to m 1 over k minus ln m as m goes to infinity, is just the definition of the Euler-Mascheroni constant, and we have this extra 1. So we have Euler-Mascheroni times minus 1. And then we can just simplify. We can use, we know that 1 is being summed n minus 1 times, so the sum should be n minus 1. Rest of the terms are just the same. We can reorganize everything, take a common denominator. N minus 1 minus 2 times Euler-Mascheroni minus 1 over 2 to the n is actually n plus 1 minus 2 times Euler-Mascheroni over 2 to the n. And then let's just write everything out for style. Integral 0 to 1, 0 to 1, n times of the fractional part of x1, x2 multiplied xn minus till xn minus 1 divided by xn is actually 1 over 2 to the n times n plus 1 minus 2 times Euler-Mascheroni constant. Isn't this such a nice result? It's very satisfying. We can evaluate lots of integrals with this. Just change the n value, and that should basically do it. I hope you enjoyed this video, guys. Let me know if this pace is good. I can reduce it down if you want. I understand I have been fast regarding my explanations these past few days. Let me know what you feel and how you like this video. I might be doing more integrals in the future if I don't find more content, which is still pretty good. So see you in the next video. Thanks for watching. Peace out.